Hi guys, this is a very brief review of trigonometry, and that's because all of you guys have taken pre-calculus and trigonometry last year, so this is just meant to refresh your memory. So I've already drawn a picture of two right triangles, right? These are the two special right triangles that you guys should be familiar with, the 45, 45, 90 degree triangle and 30, 60, 90 triangle. And each of these pictures is meant to represent like all of the similar triangles, right? There's infinitely many triangles that can have these three angles, have 45, 45, 90, and infinitely many triangles that can have the angles 30, 60, 90. And their sides, this is how you can determine what the side lengths would be, just by thinking about using different values of x that are real numbers. Okay, so we're going to derive our unit circle. You are going to need to be able to visualize your unit circle and use it as a reference in order to evaluate trig functions. And we'll talk more about that after we have finished filling it in. So we're going to focus on, well, actually first, this is a unit circle. Imagine we are in the XY plane. So the vertical axis that cuts this circle in half is the y-axis, and then the horizontal axis that cuts the circle in half is the x-axis. And unit circle, that is a circle centered at the origin. So the very center of the circle would be the point 0, 0 in the xy plane. And I'm sorry, the unit circle has a radius of 1, meaning we can figure out what some of these points are. Like this point over here that lies on the unit circle would be 1, 0. This would be 0, 1, negative 1, 0, and 0, negative 1. Okay, so to fill in quadrant 1, we're going to start by filling in the angles being measured in degrees, just because that's how we have them labeled in these special right triangles. And then we're going to figure out what the points are that lie on the unit circle for those angles. So for the angles, we have 0 degrees. This first one will be 30 degrees, 45 degrees, 60 degrees, and then up here will be 90 degrees. So if we think about drawing a right triangle, we'll do it like that. Okay, where this angle down here would be 30 degrees, right? The angle rotating off of the positive x-axis, that would make this angle up here 60 degrees. And the hypotenuse of this particular right triangle would have to be equal to 1, right? Because it's inside, the hypotenuse ends up corresponding to the radius of the unit circle. So if we go up to our 30, 60, 90 triangle, we want to think about, well, what could we make x that would make the hypotenuse of that triangle equal to 1? Well, if we make x equal to 1/2, that would make the hypotenuse of that right triangle equal to 1. So that would make this side 1. This side would be √3/2. And this side would be 1/2. So then going back down to the unit circle, the side opposite 30 degrees has a length of 1/2, and the side opposite 60 degrees has a length of √3/2. So then this point on the unit circle would be √3/2, 1/2. And I guess I'll leave the triangle and use maybe another color. Okay, so now drawing my 45, 90 degree triangle. Right, this angle would be 45 degrees. This angle would also be 45 degrees. And again, the hypotenuse of the triangle would need to be equal to 1 to match the radius of the circle. And we think, okay, well, for the 45, 90 degree triangle, what could we make x to make the hypotenuse equal to 1? And that would be 1 over root 2. So this side would end up being, the hypotenuse would end up being equal to 1, and each leg would be 1 over root 2. But we like to rationalize the denominator, meaning make the denominator a rational number by thinking about multiplying by root 2 over root 2. So 1 over root 2 is equal to root 2 over 2. So each leg of that triangle would be a length of root 2 over 2, meaning this point on the unit circle that corresponds to 45 degrees would be root 2 over 2, comma, root 2 over 2. And then thinking about rotating the 30, 60, 90 triangle, right? The side, so now this would be 60 degrees, and then the other angle would be 30 degrees. So the side opposite 30 degrees is a length of 1/2, but the side opposite 60 degrees is root 3 over 2. So the point on the unit circle would be 1/2, comma, root 3 over 2. And then you can use symmetry to fill in the other points. So sure, let's do that. So thinking about reflecting those points over the y-axis, then all the x-coordinates would be negative. So this point over here would be negative 1/2 root 3 over 2, then negative root 2 over 2, comma, root 2 over 2, negative root 3 over 2, comma, 1/2. And then if you think about rotating over the x-axis, then x and y coordinates will be negative. So negative root 3 over 2, negative 1/2, negative root 2 over 2, negative root 2 over 2, and negative 1/2, negative root 3, over 2. And then reflecting those points back over the y-axis, then the x-coordinates are positive, but the y-coordinates are still negative. Oh, that one would be negative. Okay, and then to finish filling in the angles, maybe I'll erase these triangles so that we just see the angles in quadrant 1. It's less cluttered. There we go. So I want to fill in the other angles. So to do that, I'm going to think about continuing to add 30 degrees. So like this would be 120 degrees, 150 degrees, 180 degrees, 210 degrees, 240 degrees, 270, 300, 330, and 360. And then also adding 45 degrees, or if I'll add 15 degrees to 120 degrees. So that would be 135 degrees, 225 degrees, and 315 degrees. So at this point, we have all of the angles in degrees and all of the points that lie on the unit circle. We also want to fill in the angles in radians. So it's helpful to know that, well, 0 degrees corresponds to 0 radians. And then a full rotation, so 360 degrees is 2 pi. That means half a rotation would be pi, and a quarter of a rotation would be pi over 2. Right? Because 90 degrees is half of 180 degrees, meaning 90 degrees is equal to pi over 2. 30 degrees is 1/6 of 180 degrees. So 30 degrees would be equal to pi over 6 radians. 45 degrees is 1/4 of 180 degrees. So 45 degrees would be equal to pi over 4 radians. And 60 degrees is 1/3 of 180 degrees. So 60 degrees would be equal to pi over 3 radians. Now we can fill in the rest of the angles so you know how I filled in, I thought about continuing to add 30 degrees. So like if I have 1 pi over 6 and then 2 pi over 6 is 60 degrees, which 2 pi over 6 simplifies to be pi over 3. 3 pi over 6 simplifies to be pi over 2. 4 pi over 6 simplifies to be 2 pi over 3. 5 pi over 6. 6 pi over 6 is pi. 7 pi over 6. 8 pi over 6 can simplify to 4 pi over 3. 9 pi over 6 can simplify to be 3 pi over 2. 10 pi over 6 simplifies to be 5 pi over 3. And then 11 pi over 6. And 12 pi over 6 is equal to 2 pi, which is a full rotation. And then notice if we start at pi over 3 and we keep adding pi over 3s, well, 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3 would be 2 pi. So then to fill in the remaining angles, let's think about adding pi over 4. So if we start at pi over 4, 1 pi over 4, 2 pi over 4 is pi over 2. 3 pi over 4, 4 pi over 4 is pi. 5 pi over 4, 6 pi over 4 is 3 pi over 2, 7 pi over 4, and 8 pi over 4 is 2 pi. So now we have the angles for the unit circle written in radians and degrees. Now, to use the unit circle as a reference, right? So since cosine and sine, if you think back to pre-calc and, well, actually you could even think back to geometry, so Katoa. You learned last year that on the unit circle, the x-coordinate corresponds to cosine of the angle, and the y-coordinate corresponds to sine of the angle. Now, it's also helpful to know that tangent, what color do I want to use? I'll just use black. So tangent is equal to sine over cosine. So in the xy plane and in the unit circle specifically, tangent of theta is the ratio y over x. So if we think about taking each point that lies on the unit circle and simplifying that ratio, that will be the value of tangent. I know Miss Walters made you guys write down the values of tangent. I made my students write down the values of tangent on the unit circle. Colored, I'll just use the blue. So going around the circle, I'm writing down the values of tangent. So for 0, 0 degrees, 0 radians, 0 over 1 is 0. 1/2 divided by root 3 over 2 simplifies to be root 3 over 3. Root 2 over 2 divided by root 2 over 2 is 1. Root 3 over 2 divided by 1/2 is root 3. 1 over 0 is undefined. And then we can use, notice that since the points are all the same values repeated, we can just use symmetry. So since in quadrant 2, the x-coordinate is negative, but the y-coordinate is positive, the ratio for tangent is going to end up being negative. Okay, and then in quadrant 3, since the x and y coordinates are positive, tangent will end up being, that should be negative root 3 over 3. Sorry about that. So in quadrant 3, since x and y coordinates are both negative, the ratio will be positive. Okay, negative 1 divided by 0 is undefined. And then in quadrant 4, the y-coordinate is negative, but the x-coordinate is positive, so that ratio will again be negative. I keep writing 2 when I mean to write 3. Okay, it can also be helpful to just quickly be able to identify which of the trig functions are positive versus negative in which quadrant. And I know if you've had me before, or if you had me last year, I have the little saying, which goes in the same order that the quadrants are numbered in, right? This is quadrant 1, quadrant 2, we go in the counterclockwise direction, quadrant 3, quadrant 4. Okay, so the little saying I have is all students take calculus. And that's to help you remember which of the trig functions are positive in each of those quadrants, because then whichever ones aren't positive would be negative. So the all, A, means all 6 are positive. Okay, so none of them are negative. All 6 of the trig functions are positive. The S in students means that sine and cosecant, which is sine's reciprocal, are positive, and all the other trig functions are negative. The T in take means tangent and cotangent, it's reciprocal, are positive, and the rest are negative. And the C in calculus means that cosine and its reciprocal trig function secant are positive, and the rest are negative. And that should make sense, right? You can clearly see which one's sine, cosine, and tangent, which ones are positive and negative, just because those values you're able to clearly see on the unit circle, but it would make sense that the reciprocal would follow. So it's important to have the unit circle memorized, but it's also super important to know how to use it. So remember, if you wanted to simplify or evaluate, I don't know, like, let me use a different color. Like cosine of 4 pi over 3. You would go to 4 pi over 3 or visualize where 4 pi over 3 is on the unit circle. The x coordinate there is the value of cosine. So negative 1/2 would be the value of cosine of 4 pi over 3. Oh, why am I writing 4 pi? Or if we wanted to evaluate its reciprocal for that same angle, right? Secant of 4 pi over 3, you think about where 4 pi over 3 is. Well, secant's the reciprocal of cosine, so that means that secant of 4 pi over 3 would be equal to negative 2. Okay, so you think about where the angle is and what the point is. All right, right triangle trig, where you're thinking SOHCAHTOA. Okay. So SOHCAHTOA, the S refers to sine, so like sine of theta. We use theta to represent the angle, but you could use, it's common to use other Greek letters or other variables to represent the input. So sine of theta is equal to opposite, the side opposite theta over the hypotenuse. For cosine theta, that's adjacent, so the side next to theta over hypotenuse. And then tangent of theta would be equal to the side opposite over the side adjacent. Okay, and then the reciprocal, so like since, I'll write it a different color. Since cosecant is the reciprocal of sine, would be equal to the hypotenuse over the opposite side. Secant's the reciprocal of cosine, so that would be hypotenuse over adjacent. And cotangent of theta is the reciprocal of tangent, so that would be equal to adjacent over opposite. And so if you had a right triangle, right, where we could think of this as the right angle, let's say that this angle is 50 degrees, which would mean this angle would have to be 40 degrees. Okay. I don't know, and let's say that you knew this side was a length of 12. So the side opposite, but you don't know what this side is, and you don't know what the hypotenuse is. I'll call the hypotenuse H. Okay. So you could figure out what this side would be using one of the trig ratios. So like if you wanted to use you could use tangent, it would probably be the most efficient. So you could say, okay, well, tangent of 50 degrees would be equal to the side opposite, which is x, divided by the side adjacent, which is 12. So x, that side, would be equal to 12 times tangent of 50 degrees. And you could type that into your calculator to get the approximation. And then from there, you could either use Pythagorean theorem, or you could use one of the other ratios, or one of the other trig functions to help you determine what h is. So let's move on. We're going to look at the graphs of some of the trig functions. So just sine, cosine, and tangent. Okay. So filling in the values, and you can reference your unit circle, or even better, you can visualize your unit circle to fill in the values for sine of these angles. So sine of 0 is 0. Sine of pi over 4 is root 2 over 2. Sine of pi over 2 is 1. Sine of 3 pi over 4 is, root 2 over 2. Sine of pi is 0. Sine of 5 pi over 4 is negative root 2 over 2. Sine of 3 pi over 2 is negative 1. Negative root 2 over 2, 0. So I can plot those points in the xy plane. Remember, radians are real numbers, so that makes sense for values on our x-axis. I'm going to call, what is root 2 over 2? So root 2 over 2 is approximately 0.707. Okay, so then I'm going to call this one and this negative one. Okay, so plotting those points halfway between 0 and pi over 2 is pi over 4. So 0.707 would be just below here. The tick mark would be 0.75. And then we're up to 1. We come back down. Okay, so really, we're not going to do any intense graphing with the trig functions. I'm just reminding you of what each of these three graphs looks like. The parent function, you should just be familiar. When we do curve sketching, we'll talk maybe a little bit about these graphs sketching these graphs from a calculus perspective. All right, and the domain, it's all real numbers. The range is from -1 to 1, reading the graph from bottom to top. Sine is an odd function, right? Meaning it is symmetric about the origin. A vertical reflection, it's the same as a horizontal reflection. That also allows us to say that sine of negative x is equal to negative sine of x, which can be helpful with evaluating the trig functions. And a period, right? One full, you can think of it as rotation, or like, oops, I meant to use there we go. Where all of the output values occur. So if we think about the period starting at 0, all the output values that sine has occurs and then ends at 2 pi, and then the pattern repeats. So the length of the period is 2 pi for sine, or length of the fundamental period of sine is 2 pi. Okay, so for cosine, filling in that table, cosine of 0 is 1. Okay, 0. Oh, that should be a negative root 2 over 2. That's right, there we go. And that would be positives. Okay, using the same scale for the y-axis as above. Cosine starts high, or starts at 1, then comes down. Okay, and then you could extend the graph using the pattern. Domain, like sine, is all real numbers. Range is between -1 and 1. Cosine is an even function, right? Meaning it's symmetric about the y-axis. If we performed a horizontal reflection, the graph would look the same. Also helpful to know that cosine of -x equals to cosine of x. And the period, like sine, is 2 pi. Okay, for tangent. Okay, tangent of 0 is 0. Tangent of pi over 4 is 1. Undefined. -1. 0. 1. Undefined. -1. 0. Okay, so where tangent is undefined, I'm going to draw vertical asymptotes. So graphing just the points that I have filled in. Here, I'm going to call this tick mark 1, -1. Okay, so if you remember a function approaches positive or negative infinity as it approaches a vertical asymptote. So tangent actually approaches positive infinity as it approaches the vertical asymptote from the left side, and negative infinity as it approaches the vertical asymptote from the right side. And the pattern will repeat. So I can actually extend the graph and notice the distance between those two vertical asymptotes is pi. So I can draw the other vertical asymptotes that will be on this graph. And continue the pattern of the function approaching positive infinity as the graph approaches the vertical asymptote from the left and negative infinity as it approaches from the right. Okay, so for stating the domain, all real numbers except x can't be equal to, well, we said there's a distance of pi between each of the vertical asymptotes. So if I think about like pi over 2 as being the first vertical asymptote, and then adding multiples of pi, which I can represent as pi times n, and then defining n as an element of the integer, so where n has to be an integer. So n's 1, 2, 3, negative 1, negative 2, negative 3, 0. Will represent all of those vertical asymptotes, which I've said x cannot be equal to, so that excludes those values from the domain. The range is all real numbers, reading the graph from bottom to top. The function is odd. And you could figure that out by using the fact that tangent is equal to sine over cosine. And since sine is odd and cosine is even, tangent of negative x would be equal to negative tangent of x. And the period is a length of pi. Okay, these are the trig identities you should know. You should recognize them. You should know them. When you see sine squared plus cosine squared, immediately you should think 1. Okay, let me know if you have questions on any of these, but you should be at least familiar with these identities. And then the last thing that I have in this very brief review of trig, because remember, trig was spread out over multiple chapters in your pre-calc class, is we're going to talk about just solving super basic trig equations. And what I mean by basic is by inspection, okay? So when you're solving something by inspection, it means you can just look at the equation and determine what the answer is, like what the solution is. Same thing for simple trig equations. So usually like sine, cosine, or tangent, or one of the reciprocals of x or of theta, or whatever the variable is equal to a ratio from the unit circle. And then you can state what the solution is. So, for example, the example here says solve each of the equations on the interval from 0 to 2 pi. Well, 0 to 2 pi is the unit circle. So all those angles are on there. So you're thinking, okay, well, sine is positive in quadrant 1 and quadrant 2. So in quadrant 1, what would that be? Pi over 6. And then in quadrant 2, that would be 5 pi over 6. Okay, so those are the solutions. You can also think about solving graphically. More complicated trig equations we will solve graphically on our calculators. But like if you thought about the graph of sine, I just had it drawn, but here, I'm just gonna sketch it very quickly. So just from 0 to 2 pi, so the left-hand side here is sine, the right-hand side is 1/2. Well, if we thought about a horizontal line at y equals to 1/2, the points of intersection here would be the solution. And you could, if you graphed, so if you turned the equation into a system, which we've talked about before, graph and then find those points of intersection, unfortunately, it would give you the approximation of the solutions, but for more complicated equations that you can't just solve by inspection, I'll probably be letting you use the calculator. Okay. And then cosine of -1/2. So if from 0 to 2 pi, well, cosine is negative in quadrant 2 and quadrant 3. So in quadrant 2, that would be 2 pi over 3. And in quadrant 2, quadrant 3. So quadrant 2, quadrant 3, that angle would be 4 pi over 3.